Alright, so today's lesson is an introduction to thermal energy and heat. Up until now, in school, we've been using those two terms as if they're the same thing, but today we're going to learn they're not. Okay? And there's lots of other terminology we're going to learn today. So thermal energy is very, very important in our day-to-day lives, right? We use thermostats to control furnaces. Water helps to moderate climate in certain regions, right? Winds are generated by uneven heating of Earth's surfaces, right? Weather influences the clothes we wear, right? Even the food that we consume is mostly converted into thermal energy to regulate the temperatures in our body. So what is the difference between thermal energy and heat? Well, we talked about energy, specifically kinetic energy. Kinetic energy is the energy of motion, right? And then we also have potential energy. Right? Now, thermal energy is the total kinetic energy. So you have all these particles, and they're moving around. So it's the total kinetic energy plus potential energy of all the atoms or molecules in a substance. So when I say potential energy, in this case, I'm not talking about gravitational potential energy. I'm talking about the potential energy within those molecules themselves. And for example, comparing water at 0 degrees and ice at 0 degrees. So water can exist at regular atmospheric pressure, can exist as either a solid or a liquid at 0 degrees. Whether or not it's a solid or a liquid would have different amounts of potential energy. Okay, you would have a lot more potential energy inside of that liquid form than you would inside of the solid form. So thermal energy is the total kinetic and potential energy of all atoms and molecules of a substance. Right? And as I said, it depends on the state of that substance. It also depends on the mass, like how much of it there are, the temperature, and so on. Okay. Temperature is also not thermal energy. Okay, temperature, I think I go over this here. Yeah, I'll bounce back to the previous slide in a second. But temperature is the measure of the average kinetic energy only of the atoms. So you'll have a substance and you'll have the atoms whizzing around everywhere. If you can look at the average of all of that motion, that's the temperature. If you looked at the total of it all, and not just the total kinetic energy, but that potential as well, that's thermal energy. And so it also depends on mass, like I said. So I mean, if you had, say, an iron block here and an iron block here this big compared to this big, but you could have them at the same temperature. Even though at the same temperature, the bigger one has more thermal energy. Okay. So what then is heat? Heat is the transfer of thermal energy from warmer substances to a colder one. Right? So we usually think of heat as temperature, but it's not. We also usually think of heat as a noun, but it's not. It's more of a verb, right? Talking about thermal energy moving from one object to another. And it would go from warmer to colder. Right? Thermal energy likes to spread out. Right? Just pause there. All right, so let's look at an example. Say we have 100 grams of water at 50 degrees and 500 grams of water at 50 degrees. So again, the samples have the same temperature, right? The same average kinetic energy, but the greater the mass sample has more thermal energy because it has more stuff. Right? Now, if you were to mix these together, you're not going to get thermal energy to transfer from one to the other because they're at the same temperature. Okay, you'll simply get 600 grams of water at 50 degrees Celsius. So in total, you'll have more thermal energy here than in either of the two separately. But the temperature will remain the same and there's no heat. However, if you had 500 grams of water at 50 degrees and 500 grams of water at 90 degrees, and you mix them together, now heat's going to occur. You're going to get a transfer of thermal energy. Some thermal energy is going to move from here, from these water molecules, towards these water molecules. Okay? And as they're mixed together, they will eventually end up at a new temperature somewhere in between these two. Okay? And since they're actually both exactly 500 grams and they're both water, it would be directly in between at 70 degrees. But that's called heat, when that thermal energy is transferred. And when they're at the same temperature, we call that equilibrium. So let's look at an example problem from our worksheet here. So question number 1 says, a parent places a baby bottle containing 150 milliliters of milk at 7 degrees Celsius into a pot containing 550 milliliters of water at 85 degrees Celsius. Will thermal energy stop transferring from the water to the milk at some stage? The answer is yes. Okay? I mean, thermal energy is going to always transfer from the hotter substance to the colder substance, but eventually they will reach some equilibrium. Okay, so yes, when they reach the same temperature. Let's call that equilibrium. Just pause. Okay, let's go on and talk about the methods of heat transfer. So how does thermal energy move from one object to another? There's 3 different methods. We've learned them before in science. We have convection, conduction, and radiation. Okay, so conduction is when you actually have 2 surfaces in contact. So those particles will actually be smashing into each other, transferring that thermal energy. That's conduction. And so in this case, in my picture, you have a pot in contact with this element. Okay. Convection, right, is when we have these currents. So here we still have this pot in contact with this element, which is heating the pot, right? And then the pot is also heating the water, more so at the bottom. But then, due to density, right, when the water warms up, it's moving faster, it spreads a little bit further apart and becomes less dense. And so that warm water rises, pushing the cold water down. That cold water that comes down is able to heat up, which then rises and pushes the less warm water down. And it just keeps repeating and repeating and repeating in this cycle. Okay? These are our convection currents. So this method is called convection. Lots of convection currents, not just in a pot, but in our atmosphere, in the ocean, right? They're everywhere. Last, radiation. Okay, so radiation, it's not the scary type of radiation that everybody seems to attribute when they hear the word radiation. Right? Visible light is also radiation. It's not going to do anything to you. Right? So we have this entire electromagnetic spectrum, which you learn about in grade 10 science. Things like microwaves, infrared light, visible light, and you can have the more dangerous ones like X-rays, gamma rays, things like that. But anything that has a temperature is going to give off radiation. So our bodies have a temperature. We actually emit radiation. You can't see it though, because we can only see visible light, right? But we actually emit infrared light. So in movies, you have people wear those goggles that lets them see infrared light, and it looks like this. Right? Now obviously this coffee pot is very, very hot, right? And so it looks like brighter, like red and white. But this person you can also see as well. They're emitting infrared radiation. And because of that, it's cooling them down. That's why when you go camping, they have those emergency blankets, which are very like shiny on one side. That tries to help reflect the infrared radiation back to you, and it tries to help stop you losing that heat. And there's lots of other things that we make to stop losing heat, like a thermos, right? The thermos tries to stop losing heat in all three methods, really. Two more than others, but obviously they're not clear. If you bought a clear thermos you can see through, then it can lose heat due to radiation. Right? Also on the inside, you'll have this outer layer and inner layer, usually glass, and then in between the glass and the outer layer, in this case metal, is a vacuum. Okay? That prevents conduction. It doesn't let particles touch each other. So let's try our second problem here, because I went on a bit of a rant. Second problem says, how does a thermometer work? Okay. So first you have these particles outside the thermometer, which you're trying to measure the temperature of. Right? Now those particles are going to collide with the thermometer and transfer thermal energy. Okay, so thermal energy gets transferred to the thermometer. Now inside this thermometer we have a kind of alcohol. It used to be mercury, but basically some sort of substance, right, which expands at a known rate. So what happens is the alcohol, in this case, particles move faster because they get that thermal energy, and spread out. Okay? As they spread out, they have to go somewhere, but the only place they're allowed to go is up this tube, and so they move up, spread out, and move up. Okay, and because we know the rate of expansion for thermal energy of whatever we put in the thermometers, we know where to put our little markings for what temperature it would be at. Let me pause there. All right, last thing I want to talk about are conductors and insulators, specifically thermal conductors and insulators, not electrical conductors and electrical insulators. Thermal ones, meaning thermal conductors are very good at transferring thermal energy, whereas thermal insulators are not. Okay? So metals, for example, make good thermal conductors, and other materials like plastic, things like that, are fairly good thermal insulators. Okay, like this plastic handle here on the coffee pot. Okay? And I mentioned this before. Actually, I already talked about this. But let me ask you a question. So comparing, say, metal and plastic. So I have metal and plastic in this room right now, like this, and some plastic like this document camera here. Now if I were to touch them, and you can look in your own room, look around, find something that's metal, look around, find something that's plastic, and if you were to touch them, I'm going to pause the video here, but I want you to tell me which one you think will be at a higher temperature. All right, so rephrasing the question, you're on a beach, nice 30 degrees outside, you have a metal rod and a plastic rod, been lying there on the sand for a couple hours. I think intuitively we all think that the metal rod is actually hotter. Why do we think that? Because we know not to touch it, we might get burnt. Plastic one's not going to burn us. But actually, just like this previous example, let me just go back up here, they reach some equilibrium with their surroundings, meaning the metal rod and the plastic rod both reach exactly 30 degrees. So they're at the exact same temperature. The metal rod is not hotter than the plastic. But, you know, I'm not lying to you, right? We don't touch the metal rod because it would be very, very hot. We might get a burn. So why do we do that? Take a second to think. Why do we do that if they're the same temperature? So the reason why we don't want to touch the metal rod is because it is a conductor. It's a very good conductor. The plastic rod is an insulator. So what does that mean again? Let's go over these definitions. Right? A conductor is very good at transferring thermal energy, and an insulator is not. So even though the metal rod and the plastic rod are at the same temperature, you go to touch the metal rod, it's very good at taking its thermal energy and transferring it to your hand, and it will do so quickly. Right? Whereas the plastic rod, not very good at doing that. That thermal energy, not very good at transferring it to your hand. And so even though they're at the same temperature, the metal rod will feel so much hotter because all that thermal energy goes into your hand, where it doesn't when you touch the plastic rod. Okay, so that's the reason why. And actually, there's a good video that I can put on our website that you can watch, or maybe we'll just watch it together because we have time. So let's do this question. Question number 3. This one says, would it be better to place an electric room heater near the floor or the ceiling of the room? All right, so we're going to want to heat the floor. And the reason is those convection currents, just like the one in the pot. So if we heat the floor, we promote those convection currents, meaning the air in the lower part of the room warms up, gets less dense, it goes up, pushes the cooler air down, which allows it to be heated by the heater, and those convection currents continue to go. Right? So we promote convection currents. All right.